Okay, so let's work this problem. We want to find an equation for slope and displacement across this structure. As we've talked before, you'll notice the load is a nice continuous load. So you should be able to write a nice continuous moment expression and then use direct integration to find equations for shear and displacement. So let's start with that first. So to do that, I'm going to want to cut the beam somewhere, and probably be more convenient to work on the left-hand side using our x-coordinate system. So I'll probably want to find my reaction at A. So just to help you get started with that, so we'll make a concentrated equivalent force of the entire load, which will have the value of length times the intensity, WL, and it will occur at half the length. I think you can see from that it would not be very hard to then compute by summing forces in the y direction in moments that the resulting reaction here is going to be WL over 2. Everybody see that? So now I'm going to draw a free body diagram of a cut section with the distributed load applied. Remember, it has an intensity W. This will be at some distance x. I have my reaction on the left-hand side, WL over 2, and I'll assume positive bending moment. So just like here, I'm going to come up with a concentrated equivalent of this section, which will be the length x times the height w. So this will be a function wx. And what's the distance from the cut? X over 2. I'm sorry I kind of jammed all that in there. It's hard to see. Any questions about that? So now I just sum moments about the cut, and I should be able to find a moment expression. So if I do some moments about the cut, assuming right-hand rule for my sign convention, the internal moment is positive. The concentrated equivalent for this section of the distributed load is also a positive moment. So the force is Wx, the moment arm is x over 2. And then the reaction creates negative moment of WL over 2 times x. So just rearranging my terms, I can write an expression for my moment that will be negative Wx squared over 2 plus Wxl over 2. And we can check that. Where do we know the moment in this beam? Well, yeah, the connection. So at A and at B. So at A, that's at x equals 0, I should get no moment. And if you put in x equals 0 here, you get 0. And then at L, you should have the moment at B is 0. You put in L for x, you'll see you also get 0. So it seems to match. So now that we have a moment expression that we think is good, we can solve the problem. So the first step would be, let's find the slope equation by integrating the moment divided by EI. In this problem, it wasn't stated, but we'll assume that E and I are constant. So when I look at this particular problem, you'll also notice that there's a W over 2 that looks pretty constant. So I'm going to bring that out. I'm going to have W over 2EI. And what I'm left with is the integral of the remaining pieces, which is x squared plus XL. Does that look good? So if you actually now do that integral, constant still stays there, W over 2EI. And what I'm left with is minus x cubed over 3 plus x squared L over 2, and I generate an integration constant, C1. So this is my expression now for the slope. Now, just looking at the support conditions, do I know anything about the slope at A? It's something, but I don't know what it is. It's not 0, right? What about the slope at B? Not 0. Now, I can probably guess that the slope, the displaced curve is going to look something like that. So somewhere in here, the slope will be 0. And I'll tell you right now, or give you a heads up, with a load like this that's constant, it's going to happen right in the middle. So you might look in your book and you might see the author tell you that, oh, with a constant load like that, we know that the maximum displacement occurs in the middle at L over 2. So I could actually come in here and say at L over 2, x equal L over 2, I know my slope is 0. I personally find that to be dangerous, because what I found students doing is assuming that it's always 0 in the middle, and it's not always 0 in the middle. If this load were triangular, it would not be 0 in the middle. So I think it's better to just do nothing here and carry it along, and when I get my expression for displacement, apply two conditions that I know are always true. So at this point, I'm just going to leave C1 alone. I don't know anything about the slope, and I'm just going to integrate it. So I'm going to say that y is the integral of the slope. So let's integrate this thing. So w over 2ei is still a constant. And now I get minus x to the 4th over 12 plus x cubed L over 6 plus C1x plus C2. And I have one expression, has two constants I have to solve for, but this one expression is for displacement, and I have two conditions for displacement. So let's apply those. So I know one of them is that the displacement at x equals 0 is equal to 0, right? So plug in 0 for x. 0, 0, 0. What am I left with? Only C2. So that means that C2 has to be 0. That wasn't so bad.
Where did you plug 0 in?
Into the expression for displacement. So I'm saying that the displacement at x equals 0 should be 0, but 0, 0, 0, I'm only left with C2. So C2 has to be 0.
Why would you put 0 in C1?
Well, because C1 is times x and x is 0.
I see.
The next expression, or the next condition, is that at x equal L, at B, the displacement is also 0. So let's go back and plug in x equal L everywhere. This one takes a little more time. So all these numerators are L to the 4th, but I've got 1/12 plus a 6th. What is that? That's actually a 12th, right? Because a 6th is 2/12. So I've got negative 1/12 plus 2/12. That gives me 1/12. Do you guys see that? And that 12 comes out and hits this 2. It looks like I get 24 over EI in my denominator, and then W over L to the 4th in the numerator. Does that look right? Is that what that term is? You guys buying that? And then I've got plus C1 times X, and X is L. So it looks like, and that has to be 0. So that means that C1 is going to have to be negative WL cubed over 24 EI. See that? And all I have to do is plug in this value for C1 and this value for C2 in my expression, and I'm done. So let's see what we get. Since this has this funny denominator, I'm going to go ahead and run this back through. So I'm just going to right now factor out my W over EI. So the first term will be minus x to the fourth over 24 plus x cubed L over 12 minus, so the WEI comes out and I get minus XL cubed over 24. Kind of a mess, but there it is. But now that it's all kind of packaged back together, you can see I can do some work here with my denominators. So it's not uncommon to see people go ahead and pull that 24 out, and that would leave you minus x to the fourth plus 2x cubed L minus XL cubed. Now the first thing I should do is check it. Does it match these two conditions? I do my algebra right. Well, at x equals 0, put in x equals 0, 0, 0, 0. I get 0. That's great. At x equal L, I should get 0. So I put in x equal L here, and I get 1 plus 2 minus 1. So that seems to work too. So it looks like I was able to maintain my conditions. So that should be my expression for displacement. And where is my, I don't think I ever wrote down my, now I know what C1 is. I can plug that back into here and get my expression for slope. Let's see if I can do that. All right. Again, I'm a little slow, so I'm going to run everything back in and then recollect it. So initially, my equation for slope would be minus x cubed over 6 plus x squared L over 4. And then I plug that back in. I get minus L cubed over 24. So you see, if I try to pull my 24 out here, my coefficients will change a little bit. So if I have W over 24 EI, then what am I left with? Well, this becomes minus 4x cubed plus 6x squared L minus L cubed. Now, you could find where the slope was 0, and where the slope is 0, that's going to be the maximum displacement. So how do you find where this is 0? You have to set it equal to 0, right? Might be a little tricky. Oh, I left something off. No, I messed something up. Did I mess? No, that's right. Never mind. I'm sorry. So you'd have to find these roots here. So you could do some work on this and find the values of the roots. And I think you will find that it is true that at x equal L over 2, the slope would be 0, and that would tell you where the displacement is maximum. You might encounter a problem where it says, where's the maximum displacement? And if you don't know where it is, you would have to actually come to the expression for the slope and solve for the roots where it's 0. Now, in this case, there would be 3 roots, because x is equal to 3, x cubed. but only one of them would be valid between 0 and L. You might find there's another one, I don't know, somewhere else. Or okay? So any questions about that? All right.